Okay, I think we'll get started. Is it working? Yep. Okay. Thank you, everybody, for coming to see our talk. I'm Nick, and this is Allison over here. And we're going to be presenting the work we've been doing towards formally verified contracts in Haskell. So the talk we're giving today is split up into two main sections. I'm going to be presenting the first section, where I'm going to be talking about the importance of correctness in smart contracts. That's essentially explaining the purpose of formal verification in the context of why we're doing the work that we've done so far. And the second section, Allison will be presenting, where she'll be taking you through the work that we've been working on, what we've done so far for building a foundation for this formal verification in Hyperledger Fabric. So to explain the importance of correctness in smart contracts, I want to give some context by explaining DLTs and DLTs as critical systems. So in the world of software, some systems are classified as critical systems. And some examples of this are safety critical systems. So the classic example of a safety critical system is airplane software, but it's any software where there's a threat to human life. So in an airplane, for example, if it crashes, people could die. So that is classified as a safety critical system. But more importantly, in the context of blockchain, there's business critical systems, which are anything that has any chance of significant economic losses. Classic example there is stock exchanges. And there's also security critical software. Security critical systems are any systems that have sensitive information. And they include banking systems and government systems and obviously a lot of systems like that. And critical systems, the code needs to be treated in a much more rigorous way than in non-critical code to ensure that it does what it's intended to do. So blockchain is a great use case for this because it's both a business critical and a security critical system containing high-value assets. And like I mentioned before, stock exchanges are an example of that, and also cryptocurrencies. So specifically in terms of blockchain, I want to talk about trust. So got a simple picture here of a blockchain. And one of the main selling points of the blockchain is that it's a trusted single source of truth. And this trust comes from the fact that there's a ledger of all the transactions that have happened, and this is immutable. But how that works, though, is we have a smart contract here that the transactions come through, and it's the smart contracts that actually write all the information onto the ledger. Because of that, when we talk about trusting the ledger, that doesn't really make any sense if you don't actually trust the smart contract, and therefore the code that's in that smart contract that is writing the information into the ledger. So to tie this back to what I was saying about critical systems, since blockchains are critical systems, you need to be able to trust the smart contracts since they are the ones that are kind of governing the trust in the network. So another way of saying that, just like with Gandalf, the smart contracts are the gatekeepers to the ledger. So if you're not trusting the smart contracts, the trust in the network is not there. So in talking about this trust, what's the problem with the current smart contract languages to achieve this? So for those who aren't overly familiar with Fabric, we currently support 3 smart contract languages: Golang, Java, and JavaScript. And these are all general purpose imperative languages. And these languages are prone to exploits and bugs that are not well suited for critical systems. So there's some classic examples of this that I'm sure you've all heard about, like the DAO attack and the parity attack, both on Ethereum that cost lots of money. And in general, though, not just these high-profile attacks, but all these subtle bugs and exploits are not acceptable in critical systems, and especially in enterprise use cases, like we deal with on Hyperledger Fabric. To elaborate on this point a little bit more, I want to refer to this quote from the director of engineering at DAML. Basically saying, for critical systems, blockchain is not a viable option if you can't trust the smart contracts, because in like financial markets, like they work with at DAML, but also other industries that are critical systems, you need to be able to trust the blockchain and the smart contracts and not introduce new sources of risk into your domain. So talking about this, how can these problems be solved? So the solution is functional programming, and we're not the only ones that think this. Here's just an example of some logos of some other blockchain companies that are also using functional programming for this. And yeah, so let's see. I'm saying functional programming is the solution right now, but I haven't explained how at all. So let's go into that. So we're saying to trust the ledger and to trust the blockchain, you need to be able to trust your smart contracts. And your smart contracts are essentially just code. So how can you trust your code? So at the bottom here, you can see I have this spectrum of confidence. And the main way for doing ensuring correctness of code today is using static typing and static verification. And there's varying levels of how you can achieve that. To the left of the spectrum, there's simple types, and they include languages such as Solidity and Go and Java. Pretty much most imperative languages that have typing are classified as simple types in this context. But then further up the spectrum, we have languages like Haskell and other strongly typed functional programming languages that give you a higher level of confidence due to how their type system works. So that's kind of without performing formal verification yet. You still have a higher base level of confidence in your code due to how Haskell's type system works. And then there's a level on top of that, which is formal verification, which I'll be getting to a bit later. But looking at this, there's one thing that might be coming to your mind. What about testing? In the software engineering industry, we obviously perform testing a lot to make sure our code is correct. Why am I not talking about that in the context of this here? And for that, we agree with Dijkstra. So Edgar Dijkstra here is a famous computer scientist from the 1960s who has done a lot of work around distributed systems as well as formal verification. And this quote is essentially saying, when you're writing tests, you're testing specific instances of a runtime of a function or some piece of software. And you can sequentially eliminate some certain executions of that function to be incorrect, but you can never provably know that there are no bugs in the system. So like he says, you can find the presence of bugs through testing, but you can never show their absence. And that's kind of the core of why, when we're talking about critical systems, testing is inadequate. So that being said, don't get me wrong, we're not saying testing is bad and it shouldn't be in the software engineering industry. That's not true at all. It definitely has its place, but we don't believe that place is in critical systems, where the correctness is more important than some everyday software. Yes, so what is formal verification? I've been mentioning it a few times. So I've got the definition up the top. I won't read that. But essentially, what it does is you have a formal specification which specifies how a certain piece of code should behave and how it is correct. And that specification will then, under the hood, use what are called formal methods to then mathematically prove that the code you were writing a specification for is doing what it's intended to do. So this is the inverse of testing, where rather than just, like I mentioned one at a time, eliminating certain input values that could be incorrect with the code, you're mathematically exploring the whole state space of a function mathematically. And the other important thing about this will happen statically and not at runtime. And you'll get a guarantee whether the code is conforming to that specification or not. So one of the main popular techniques for performing formal verification is called design by contract. And essentially, the contract is the specification that I was mentioning on the previous slide. And that contract will have certain things in it, these dot points down below, that will specify how a function needs to behave. So preconditions are essentially just guarantees on a certain properties for the input values of a function, and similarly postconditions for the output values. And then invariance. So an invariant is something that will be invariant through the whole lifetime of some certain scope in a function or some piece of code. And by invariant, I mean it's something that won't change. So you can specify some property. In our case, as we're about to see in an example, will be a function. And throughout the lifetime of that function, we can specify some property that will be constant throughout the whole lifetime of that function. And that's useful for preventing bugs and exploits. And we're going to look at an example of an invariant right now. an invariant that could have prevented the DAO attack. So here I have a simple Solidity contract. It's just a crowdfunding example to illustrate how formal verification could prevent reentry attacks. And a reentry attack is the specific, the technical term for the attack that was actually used for the DAO attack. So in this function here, it's pretty simple. You can see on line 2, it's a crowdfunding thing that has some amount of shares, and those shares can be contributed by multiple users. And then we just have a withdraw function that lets a user withdraw some of the shares out of their account. Obviously making sure on line 4, just a simple check to make sure they're not drawing out too much, withdrawing the money, and then on line 7, it updates the shares to the new amount, subtracting what the user has withdrawn out of the fund. Now this code here is vulnerable to a reentry attack. We're going to go through how and why, and then show how formal verification, and specifically how an invariant, could have prevented this from happening. So this is the intended execution of this contract and how the developer of this contract intended it to work. So on that line 5, where they do the call and withdraw the amount, that goes to an end user who receives that money. And then after they receive the money, the function call will return back, and then the shares will get updated after that. However, since the shares are updated after the call to actually withdraw the amount, that is the reason why we can have a reentry attack. And how that could work is the target of the call, instead of being a user, could be another Ethereum contract. And that Ethereum contract could be a malicious one that actually, instead of just receiving the money that was intended by this fund, it can actually, while the runtime of that contract is being executed, the fund contract, they can actually re-enter and call back into the function and keep doing that and drain the money out of the account. And this process of a malicious contract receiving a call like on line 5 and re-entering into the contract while it's still executing is essentially how the DAO attack happened. So how could we have prevented such a thing happening? This is exactly the same contract, but instead I've specified an invariant on line 1. This is a pseudocode, so this is not actually how you would write it, but just for simplification and to show the concept, I turned it into pseudocode. But basically, this invariant is saying that the amount of shares in the fund minus the current user's user balance needs to stay constant throughout the runtime of this function. And because of that, and like I mentioned before, this formal verification happens statically at runtime, with that invariant in place, when you perform the formal verification, it would fail, and it would tell you that I can't guarantee that this invariant will always hold for any possible runtime of this function because a reentry attack could happen on line 6. So this invariant kind of saves you, and what it will tell you is if you just put the shares, so here down on line 8 we have shares minus equals amount. If we put that before the call, so that the shares data gets updated before the call, then if that re-entry happened, it would fail because the invariant, sorry, I explained that not quite right. Because the shares amount is before now, the re-entry attack can't occur because if the call came back in, it wouldn't work because the shares had already been updated. So this is a simple example of formal verification. And once again, just like with functional programming, it's not just us doing this. All our friends that we mentioned on that previous slide are also doing this as well. So that leads me to concluding kind of what I've been showing so far about why another smart contract language for Hyperledger Fabric. So hopefully by now I've convinced you that smart contracts contain business critical and security critical code, and therefore it's important for them to be correct, and correct means no bugs and also no exploits. The current state of the art for ensuring correct code is functional programming and formal verification. And the ability to have confidence in smart contracts, confidence that they are correct, we believe is worth creating a new contract language for. So before I hand it over to Allison to show you through the work we've done so far, first, to tie it all up, I want to give a brief introduction to functional programming in Haskell. So for those that aren't familiar, the core concept behind functional programming is that your whole programs are built up of mathematical functions. And mathematical function has a few different names. You may have heard it called a pure function or a deterministic function, and they all mean the same thing. So, and what they mean, so mathematical function basically means if you give the same input to a function, you will always get the same output, and nothing else will happen. So an illustration of that just at the bottom here. So a pure function, you give it an input, and the output will always be the same. However, with an impure function, other things can happen as well. And these other things that could happen that could change the result each time are called side effects. So let me go into a bit more detail about what these side effects are and why it's important for them to be controlled. So before I move on, actually, another important point here. So in Haskell and other functional programming languages, it's purely made up of mathematical functions, like I've mentioned here. And an outcome of that, the fact that they have to be pure functions, means that running side effects in the program have to be controlled and managed by the language runtime, which is an important point for formal verification as well, which we'll get to later as well. So side effects. So the reason we call them side effects is because in mathematical function terminology, there's a main effect. And the main effect of a function is returning a value, the output value of the function. So anything else that the function does that is observable outside the scope of the function is classified as a side effect. So examples of that, performing I/O, mutating data, or even just calling another function within itself that in turn performs some side effects. So an example of what these side effects are, so here is just a simple JavaScript function I wrote. I first want to say this is terrible code, and I'm not endorsing this in any way, but this is just to illustrate some different types of side effects. So this function is just an add name function that will add a new name to an array, the array up on line 1. And you can see on line 4, so that's already a side effect. It's accessing a global variable outside of its own scope. And then it's performing another side effect on line 5. So it's doing some I/O operation. We have no idea what it's doing, but it's doing something and then returning a Boolean. And that, therefore, is a side effect. And then on line 7, we're mutating the global variable based off that Boolean that's returned from that I/O operation. And furthermore, this function doesn't even have a main effect. There's no return value. So this simple function illustrates 4 different types of side effects. And in Haskell and other functional programming languages, it's not possible to write any of these types of side effects in an uncontrolled way that aren't specified by the type system. OK, so that's a brief introduction to functional programming. Haskell. So it's a purely functional language, like I mentioned, which means all the functions are mathematical functions in a language. It's not possible to write an impure function. It's strongly typed. And I won't go into too much detail about the algebraic data types, but it's basically just the way of Haskell has for kind of structuring the application and have everything fit together in a composable way. And I will explain this brief function syntax, because shortly Allison will be showing you some Haskell code examples. And if you haven't seen it before, hopefully this will make it not so scary. So here I have just a simple function definition called f. And that first line is the function signature, the type signature, which tells you that the function takes 2 integers, and then its output value is an integer. And then on the next line, you can see what that actual function is. It takes the 2 integers, which I've called x and y, and just returns the sum of them. And then also function invocation in Haskell also looks quite different to what you may be used to from imperative languages. So instead of calling the function f and then putting it in brackets and then comma separating the input values, it's all just space separated in Haskell, like you can see at the bottom there. So how do these tie together? I've explained formal verification, and I've also separately explained functional programming and said that they're important for ensuring correctness. The reason why these 2 things are very much connected and related in this way is because functional programming languages are very amenable to formal verification. A big reason for that is because functional programming and formal verification both have their foundation in mathematics. And due to all the functions in Haskell being mathematical functions, makes the formal methods, or the mathematical methods that are run under the hood in formal verification, a lot easier to perform. And Haskell in particular, we just chose as is a popular choice because it's the purest mainstream functional programming language. And all those logos I showed you before, the other people also doing these things, the vast majority of them are also doing it with Haskell. So with that, I'll hand it off to Allison, and she will take you through the work we've done. And yeah, thank you, Allison.
Thanks, Nick. Can everyone hear me OK? So for the second half of this talk, I'm going to be describing what it takes to build a new smart contracts language in Hyperledger Fabric, and in particular, the work that we've done in providing Haskell support in Fabric. So just a note, in Fabric, smart contracts are called chain code. So from now on, smart contracts equals chain code. All right, so just to provide a bit of context, this is a very basic overview of the Hyperledger Fabric architecture. It consists of several application clients that connect to a network of peers. These peers communicate with the chain code, which is a user-defined business logic that dictates how the ledger is updated. And that's all coordinated through the peer. So the client collects a series of responses from the peer on a transaction proposal, and then forwards the transactions onto the ordering service that sequences the transactions into blocks and then sends the blocks back to the peer to update the ledger. So because the chain code is the gatekeeper to the ledger, that's the bit that we're most interested in, and all of that coordination happens through the peer. So we wanted to fully understand how this chain code peer relationship works. So a bit more detail on the Peer-Chaincode Architecture. The peer and the chain code run as two separate processes. There's several advantages for this. The first one is that the chain code contains user-implemented code, so untrusted code. So there's failure isolation in the case that it crashes. But importantly, it allows for tech stack independence and language independence. It means that we can write the chain code in a completely different language than the peer code is written in. And all that's required is that there's some standard of communication between the two of them. So the peer and the chain code communicate via gRPC. They send protobuf messages, chain code messages between the two of them. This is initially set up with the register message that's sent from the chain code shim. And the chain code shim is like this wrapper that coordinates all of the interaction between the peer and the actual user implementation of the chain code. I just want to note here that this architecture is specific for the user chain code. There's also system chain code in Fabric, and that works a little bit differently. So this is just an example of some communication that can happen between the peer and the chain code. So the peer will send a transaction that calls an invoke on the user chain code. And if, as a part of the execution of that user chain code, the chain code requires to interact with the ledger in some way, for example, to get state from the ledger, it will make a call back to the peer. The peer will then get the state from the ledger and return that in a response. Then the user chain code will continue its execution and ultimately return with a completed message. So there are actually many more different types of messages than the ones shown on the previous slide, all with different functions. So the ones in orange here are used to set up initially that Peer-Chaincode communication. So the chain code will send a register message, and the peer will respond with a registered and a ready. And this will put the chain code into a state where it can start to accept transactions. The blue messages are just the generic messages for sending transactions and their responses. And then if as a part of the execution of the user-defined chain code, it requires to interact with the ledger in some way, it'll send one of these response types in green. We just have two examples here, get state and put state, but there are actually many more different types of messages that the chain code can send back to the peer. So in this case, get state, put state, they're pretty self-explanatory, just putting state to the ledger or getting state from the ledger. So when these run, when these are called back to the peer, the user execution of the chain code will actually pause and then wait for a response from the peer. It will then continue in its execution and then either send a completed or an error message. So the point of this is that what goes on in the chain code process is actually a little bit more involved than just simply running the user code. Because the chain code has to be a state machine. It has to know when it's in a state that's ready to accept transactions. And then it also has to coordinate sending these calls back to the peer and receiving responses. So the component of the chain code that deals with all of this complexity is called the shim. And it's actually made up of a bunch of different components within it. So it has a setup and coordination piece, which initially sets up that communication with the peer. There's a gRPC client that sends and receives messages, and then a handler which routes the messages to the correct functions. There's what's called the chain code stub, which is an interface. The chain code stub contains the entire context of a transaction that is sent to the chain code. This includes things like the transaction ID and the payload of the transaction proposal. And it also contains a whole suite of methods that allow the user to interact with that context in some way. So these can either be local to the chain code and do things like get the transaction ID or get some details of the transaction proposal, or they can also be methods that allow the chain code to interact back with the peer, so the get state, put state, for example. And finally, there's the chain code interface, and this defines the two methods that the user-implemented chain code need to implement, which is invoke and init. And finally, with all of these pieces, then you have the user-implemented chain code on top of that. And it was really this user chain code that we wanted to enable people to write in Haskell. But to do this, because the chain code involves all of these other things as well, we had to make some design decisions about how this would work. So we had two main options. The first one was to leverage one of the existing code bases out there, so use as much code that's already in existence as possible. So to do this, we would use the Go shim, and from that, we would take basically the gRPC communication portion of that. And then because Haskell is such a strongly typed system, it would be required that the Haskell part of it would know about all of the type signatures of all of the stub methods. So we would have to implement that portion of it anyway. And then the Go and the Haskell would interact via function calls between them. The other option was to just re-implement the entire shim in Haskell. And this was the option that we went with in the end for a few reasons. It meant that we didn't have to deal with the overhead of having two separate processes running, one for the Go and one for the Haskell, and then dealing with those foreign function calls between the two of them. But it also has the benefit that the entire shim is then type safe. And down the line, we'll be able to formally verify both the shim and then also allow formal verification of the user chain code. The other benefit is that it is the same model that was used with the other chain code languages in Fabric. So Java, JavaScript, and Go all have the entire chain code written in that language. And just as a reminder, in order to have the entire chain code in Haskell, it meant that we needed to implement all of these shim components in Haskell as well. So the approach that we took to do this was to use the Go code as a base to port across into Haskell. But Go and Haskell use two very different programming paradigms. So we had to change the imperative object-oriented Go code into pure and functional equivalents in Haskell. So this meant making everything type safe. We had to change all of the statements to expressions. We had to get rid of mutable variables, and we needed to handle side effects in a controlled manner. So in Go, the mutable state is done through mutable structs, and in Haskell, this needs to be done with state monads. So I'll just give an example, quick example of what this process looks like. This is one of the handler functions of one of the stub methods in Go. You can see immediately from the function's signature that it's not clear that there are side effects that are happening within this function. So it takes a bunch of parameters and it returns a byte array and an error. within the function body, there are multiple statements in here, and you can see on line 5, there's this call peer with chaincode message method call. And within this method, there's actually some I/O happening, there's some state mutation happening, all of which is not clear just from looking at that code. So this is the equivalent getState function written in Haskell. From the function signature, it's immediately clear with the output type as the I/O monad that there is side effects happening within this function. All of those statements that you saw in the previous example have been converted to a single expression. And so having code written in this way, this pure way, makes it easier to reason about what this function is doing. And it makes the code more composable and more modular, and overall, it just makes the entire program more understandable. So of what we have done so far to enable Haskell chaincode support so far, we've done all of the startup and coordination piece of the Shim, all of the gRPC communication. So this included the encoding and decoding of protobuf to Haskell, the gRPC client, the message handler, which takes the messages, receives, and routes them to the correct function. In terms of the chaincode stub, we've implemented 15 out of the 36 methods so far. In terms of what's left, there's just 3 core functions, and these are the state iterator functions like getStateByRange. So the 21 methods that are left, most of those are just derivatives of these 3 core functions. So the Shim is completely functional, it's working. So we can start writing some user-defined chaincode. So we've done that. We've recreated one of the common examples that's used in Fabric, which is the fab car example. It tracks car ownership on the blockchain. So I'll show you what one of the methods from the fab car example looks like in Haskell. So this is the change car owner function. Again, you can see from the function signature that it returns an I/O, so there's side effects happening in here. On line 4, you can see that it makes a call back to the peer to get state from the ledger. When it receives a response, it will then create a new car instance with the new owner. And then on line 12, you can see that it puts that state back to the ledger. So this is an example of a function that makes multiple calls back to the peer. And it's all done in a single expression and in a pure way. So from this, you might be wondering when you can get started writing your own Haskell chaincode. And I'm pleased to say that all of our work is now open source. So just know that this is experimental at this stage. It's not feature complete. But this repo contains documentation on how to get started, as well as some simple examples of chaincode. So we encourage everyone to please fork it, test it out, try writing your own chaincode in Haskell. If you find issues, raise them. If you want to contribute, feel free to open a pull request. Importantly, give it a star. We want to get this out into the community, get as many people testing it as possible so we can start getting some feedback. So in conclusion, we hope that we've convinced you that blockchains are critical systems, and therefore it's vital that the smart contracts are correct. Formal verification is the current state of the art to ensure code correctness, and functional programming provides a good foundation for formal verification because of their shared roots in mathematics. So we've implemented support for Haskell chaincode in Fabric, and we believe this is the first step to being able to provide formally verifiable chaincode. So we're not done yet. As I mentioned, we still need to finish implementation of the stub functions, so 3 core functions left to go. We need to add support for concurrency in the chaincode. And finally, we need to implement formal verification of both the Haskell Shim and also enable formal verification of the user-defined chaincode. We'd also eventually like to get Haskell officially accepted as one of the Fabric languages, smart contract languages. So if you can take anything away from today's talk, we hope it will be this. Smart contracts are important as a gatekeeper to the ledger, so they need to be correct. And we believe that formal verification and functional programming is the way to go to achieve this. So we have a few minutes left of this session. I don't want to keep you between beer, but I guess we have time for a couple of questions if anyone has anything. Yep.
There's a reason you went for vanilla Haskell versus one of the Haskell-derived languages that you showed?
Like with DAML, for example. Do you want to?
Yeah, sure. I can take that one. So like I was saying before, we wanted to add Haskell support as a language just like the three existing ones. And the way those are kind of working in Fabric today is their general purpose to do any kind of domain or anything like that. So JavaScript, Java, and Go are all general purpose languages. And we did consider like a DSL, like you're asking about, but we figured if we kind of added support in that way and made a specific DSL for a domain, like DAML was for the financial services area, it wouldn't really match the way the support of the other three languages are supplied. And we thought, in terms of getting people onboarded and using the language, we wanted to kind of make it as similar to the existing ones as possible and just have it more general purpose. Yep.
So, follow up to your question. In the presentation just before you guys, Jonathan Levy showed how he saves state of DAML execution in Fabric. So the logical conclusion, the logical follow-up to that is to have a shim in DAML so that DAML executes as part of chaincode, right? So that not only that you save steps of DAML, but the actual execution is within the chaincode. Right, but that would make the whole picture complete.
Yeah. Do you have something to say about it? Yeah. So you go.
That would be a great achievement.
Yeah. Yep. That sounds good.
Another short question. Now, if the language is formally verifiable, and did I understand correctly that I cannot read or write state, then how do I do it through even the chaincode?
So the state is stored in the actual ledger. So the chain code itself is stateless, apart from the fact that it records whether it's ready to receive transactions. But apart from that, in terms of all of the transaction proposals that come through that chain code process, none of that is stored locally. So the chain code itself, the Haskell portion, is stateless. And then all of the state is sent to the peer, through the peer to the ledger.
But I can call the peer for how to get state.
Yes.
That is agreed.
Yes.
That's enough.
Yep.
Great presentation. Thanks very much. Dan Salmon from the Accord Project. Just wanted to cheekily get people a signpost to my presentation tomorrow. Or show Ergo running on Fabric.
Okay. Cool.
Great.
People are interested.
Yeah. We had you listed as one of our friends.
Thank you very much. It's a slightly different approach. Ergo is implemented in Coq,
Yeah.
but also from the same stable.
Cool. Looking forward to it.
In terms of speed, the Haskell version is the speed up or speed down rather than public Go version.
I don't think we haven't done any performance tests of the way that Haskell will run. We still need to implement the concurrency portion of the Haskell. So I think that time will tell. The Haskell has a very elegant way of dealing with concurrency. So we're hopeful that when we do implement the concurrency in Haskell, that it will actually be able to process transactions faster. But we can't tell you just yet. We'll let you know.
Yeah, I think it's pretty rare that the performance bottleneck is the user chain code.
Yeah. So I was going to say, yeah.
Yeah.
Yeah. The bottleneck and
Yeah.
yeah, I agree completely. The bottleneck is really the actual language. It's the actual resolution of the blockchain network.
All that geography.
Yeah. Yep.
Yes, I'm interested in the specifications that you're talking about for the
Not at this point, no. So like I said, we're still kind of building the foundation of like fleshing out the rest of the Haskell support first. And then we have some ideas of different, like, because there's various ways to perform formal verification in Haskell. In general, that design by contract that I presented is kind of the main approach for formally verifying functions. So we'll probably be doing some approach like that, but regarding details, we haven't yet chosen the exact approach we want to take with that, and therefore haven't come up with best practices design patterns. But there are, so I mentioned the DAO attack as a reentry attack, and there are some other well-known like types of attacks that can happen, like overflow and underflow and things like that. And just the general, like a good design by contract formally specified specification, I guess, would protect you from all of those as well. So invariants can also help with over and underflow attacks. And then the pre and post conditions can help as well. So the design by contract idea of doing formal verification would be the way to go, but beyond that, we don't have specific examples, if that's what you're asking.
I guess I'd ask you, is it trivial to sort of specify that concept? Like, is it something that anybody can now?
I see.
Or is there like
You do need to have some expertise and knowledge in formal verification to know what and how you need to specify a certain piece of code. So it does require some upskilling, I guess, for someone to be out, for the everyday programmer to be able to start formally verifying code. There's a bit of a step there, but hopefully with examples and more people getting on board, like Accord, that process will become easier. Yep.
So leading on from that, your answer to that, how do you verify some of the customers? We discussed the knowledge process in building this new chain code. But what kind of tools and frameworks have you used to formally verify what you wrote?
So we haven't got to the step of actually doing the formal verification yet. So like Allison presented, we're building out the foundation and having this whole Haskell support, because Haskell is a very amenable language for the formal verification. But we're not quite at the point of actually having that. Well, we're still completing the actual shim, and when that is done, then we'll start exploring the different ways of doing formal verification. But the user chain code example that Allison showed of the fab car, that is not being formally verified. It just has the level of verification that you get out of the box from Haskell, which is still a step up from the other languages, but there's no full formal verification happening yet.
All right, I think that beers might be happening out there now. So we'll be around tonight and for the rest of the conference. So if you have any more questions, feel free to come ask us.
Thank you.
Thanks.